In this next video, we're going to go over the remainder of the gas laws that use only a few of the possible variables of pressure, temperature, volume, and number of moles, but we're keeping some of the variables constant and changing other variables. This is very similar to the two laws that we looked at in the last video, Boyle's law, where we were changing pressure and volume while keeping number of moles and temperature constant, and Charles's law, where we were changing volume and temperature while keeping moles and pressure constant. The next one to look at is Avogadro's law. Avogadro, we remember from the idea of the mole, found that equal volumes of gases contain an equal number of particles as long as the pressure and temperature is held constant. So this is a direct relationship between the volume of the gas and the number of moles. So we can write the equation for Avogadro, V over N equals K, or V1 over N1 equals V2 over N2. Now, volume here can be in any units as long as they're consistent, and should always be in moles. So let's look at some example problems of Avogadro. A 6-liter sample at 30 degrees Celsius contains 0.5 moles of a gas. If an additional 0.25 moles of gas at the same pressure and temperature are added, what is the final total volume of the gas? We're going to use Avogadro here because we're changing volume and moles. V1 over N1 equals V2 over N2. So our V1 is 6.0 liters. Our N1 is 0.5 moles. Our V2 is what we're trying to find. And now we have 0.75. So we're going to cross multiply 6.0 times 0.75 equals V2 times 0.5. So we get 4.5 equals V2 times 0.5. V2 is therefore equal to 9.0 liters. Another example. 32 grams of oxygen gas has a volume of 18.5 liters. What mass will a volume of 25 liters at the same temperature and pressure have? So once again, V1 over N1 equals V2 over N2. You can see we have change in volume here. We also have grams. So we first need to convert grams to moles. 32 grams of oxygen. Remember, oxygen is a diatomic. So its molar mass is actually the same, 32. So we get 1.000 moles of oxygen gas. So 18.5 liters divided by 1.00 equals 25.0 liters over N2. Cross multiply 18.5 N2 equals 25. The number of moles here, 25 divided by 18.5, which comes out to 1.35. Now we got to convert that back into grams. One mole, 32 grams. You get a final answer, 43.2 moles. Or 43.2 grams of oxygen, sorry. Another law is known as Amonton's law. Amonton's law was actually known as Gay-Lussac's law for a long time, and you'll actually see it all over the internet and in textbooks were listed that way. The research has shown that Amonton actually came up with this law first, so the more updated versions show this as Amonton's law. It shows the direct relationship between pressure and temperature when moles and volume are constant. So in this case, we get P1 over T1 equals P2 over T2, or P over T equals K. Remember, temperature must be in Kelvin. This is very important anytime you're using temperature in gas laws. Here, pressure can be in any units as long as they are consistent. So let's look at an example of this. A 25 degrees gas at 25 degrees Celsius has a pressure of 1.5 atmospheres At what is the temperature of the gas in degrees Celsius if the pressure is increased to 2.75 atmospheres? So P1 over T1, P2 over T2. So we get 1.50 over 298 Kelvin. Remember, to get to Kelvin, we add 273 equals 2.75 over T2. Cross multiply. So 298 times 2.75 is out to 819.5. So we have 1.50 T2 equals 819.5. T2 is therefore 546 degrees Kelvin. Subtract 273, and the new temperature would actually have to be 273 degrees Celsius. So a huge increase in temperature to get that big of an increase of 1.25 atmospheres. Make sure that you're converting to Kelvin before doing any gas law problems, then you can convert back to Celsius. We also have something that involves 3 variables, just like we had Charles's law that was 2 variables, Boyle's law that was 2 variables, Avogadro's that was 2 variables, Amonton's that's 2 variables. We also have the combined gas law, which combines Charles's law and Boyle's law. Remember, V over T equals K for Charles, P times V equals K for Boyle. So the combined gas law is going to be the 2 of them combined together. P times V over T equals K, or P1 V1 over T1 equals P2 V2 over T2. So let's look at an example of this. A sample of gas at 25 degrees Celsius and 1 atmosphere has a volume of 175 milliliters. At what temperature will the same gas have a volume of 225 milliliters and a pressure of 2.25 atmospheres? Now, I actually find, once we get to 6 variables in the equation here, P1, V1, T1, P2, V2, T2, that it's easiest to do the algebra first. So I'm going to cross multiply P1, V1, T2 equals P2, V2, T1. I'm trying to solve for T2, so T2 is P2, V2, T1, divided by P1, V1. Then I can plug in my values and not have to worry about doing the algebra with all those numbers involved. So T2 is equal to P2, which is 2.25 atmospheres, V2, 225 milliliters, T1, 298 Kelvin, 273 plus 25. Remember, Celsius always must be converted to Kelvin. 1.00 atmospheres is P1, 175 milliliters is V1. So 2.25 times 225 times 298 divided by 1 divided by 175. I get a T2 in this case, 862 Kelvin, which would be 589 degrees Celsius. To summarize our gas laws, we'll go back through the list and look at what we're talking about with each one. We have Boyle, P times V equals K, N and T are constant. So this is our relationship. Which is indirect. And these are our constants. Next one, Charles, V over V over T equals K, which is direct. P and V are my constants. Avogadro's V over N equals K, which is direct. P and T are my constants. Amonton's P over T equals K, also direct. N and V are my constants. And finally, the combined, which has both a direct and indirect relationship in it, PV over T equals K, in this case just N being held constant. In the next video, we'll look at the ideal gas law, which puts all of these together and is actually where all of these are derived from, which involves all four variables with no constants.